Hi everyone, welcome to the Data Platform Summit. My name is Denis, and today my session will be SQL Server Query Lifecycle. As I said previously, my name is Denis Reznik. I'm from Kyiv, Ukraine. I'm working in top company as a data architect, and I'm holding Microsoft MVP status for the last 13 years. I love performance tuning and database internals very much, and in this session I would like to share my knowledge about SQL Server internals. So, in this session we will follow the path of SQL Server query from the moment of time when we are sending query to the SQL Server to the moment of time when we are receiving results back. On this path, we will go through all SQL Server main components: network interface, query processor, storage engine, and SQL OS. And an entry point for us will be SQL Server network interface. This is a protocol layer which establishes connection between client and database. So, for data transferring between client and server, SQL Server use tabular data stream protocol. And for these purposes, SQL Server has three endpoints. One for each protocol: shared memory, TCP/IP, and named pipes. Shared memory used for local connection, TCP/IP and named pipes for network connection. When your application establishes connection with SQL Server on one of the endpoints, it sends TDS package to the server. And inside the TDS package, the main component of it is query text. So it's time for the first demo. On this demo, we will connect to Stack Overflow database. We already connected to the server. Right now we are connected to the Stack Overflow database, and we will run few queries. So in this demo, in this example, my Management Studio is a client and my SQL Server instance is a server. Right now I'm sending query to the server and I'm receiving results almost immediately. Yes, it took less than 1 milliseconds. Let's try to get more results. 100,000. Now it's taken a while. 1 second, 2 seconds. It's finished. A lot of results returned, and the execution time is 2 seconds. But at the same time, you see that CPU time is 500 milliseconds, which means that SQL Server was executing this query for 500 milliseconds and 1.5 seconds spent on something else. Let's try to find where it spent so much time. I'm going to use DMV exec session wait stats, and I will get the wait statistics particularly for my session. As you see here, the main wait is async network I/O, which sounds related to the network. But in this case, it's not true. Since I'm using my local server, I will be using a shared memory endpoint and shared memory protocol for accessing data. I can check this with DMExec connections view. So let's check my current connection, and you see that protocol is shared memory. So in this case, I should not have any network latency for accessing my data, but I'm spending 1.5 seconds for this wait. Let's go back to the presentation and I will show where we are spending so much time. This slide is an explanation of what was happened on demo. Let's say we have a select query which reads data from users table And this is an example of .NET execution code. SQL Server have to read the data. And here we are touching the topic of SQL OS a bit, because SQL OS is managing CPU resources for the queries with schedulers. Let's say the query should be on scheduler to get CPU time and to execute. Scheduler is taking the query from the queue and starts executing. Query is reading the data and sending first batch to the client. And at this point, SQL Server understands that it's not going to waste CPU time until client is handling the results of the query. So SQL Server put the query into the suspended queue with async network I/O wait. At this time, SQL Server is waiting for the client to request the second batch. When it is requested, query is going to the runnable queue and then continue its execution. And the time spent in suspended queue is our async network I/O wait. The reason of high async network I/O wait can be the poor logic on the client like this, when we have thread sleeping between reads, or just enormous amount of rows, like we have in our demo. Management Studio have to render all that data, and SQL Server should not wait while Management Studio is rendering big amount of rows. Okay, that's all for SQL Server Network Interface, and we are going to the next topic, query processing. Our final goal is to get the data from database, and query processing is a very important part of that path, because before taking data from disk, SQL Server needs to understand which data it needs to process, where this data is located in which tables, and how to do this as fast as possible. So query processing is doing this, and query processing consists of several parts. First part is parser. Its purpose is to parse SQL query, validate syntax, and create SQL handle based on that query text. It can be considered as a hash, and with which we can check if query plan is already created for that query. Plan cache can be considered as a hash table and SQL handle as a key. So we can quickly check if there is query plan in the plan cache, and if it is there, we're going to the last phase of query processing, which is called executor, where we are starting the query execution. If there are no query plan in the cache, we need to create it, because query plan is the instructions where to take the data and how to take the data, in which order, and so on and so on. So, if there are no plan in the cache, parser will create parse tree and give it to the next component, which is called algebraizer. Algebраizer's goal is to validate that all objects referenced in the query are accessible in current execution context, validate the data types for each node in the tree, and create an object which is called bound tree or query tree, which is a logical representation of the query. And that object will be an input for the main component of query processing, optimizer. Optimizer's goal is to create the query plan, which will be used for query execution. And when this plan is compiled, SQL Server save it to the plan cache, where it will live for a while. And then, again, we are going to the execution phase, and SQL Server starts executing the query. Okay, that's all for query processing, but I would like to dig a bit more inside Optimizer, which is the main component of query processing and maybe the main component of the SQL Server engine. So, the goal of optimization is to create the best possible execution plan. And at this stage, we are not executing query and we don't know anything about the query runtime statistics. So SQL Server needs to build plan based on some estimated values. And SQL Server tried to do an estimate for I/O, CPU, and memory consumption. Actually, estimated CPU is the actual, can be considered as an actual execution time of the query. And this artificial value, query cost, will be used by optimizer to compare the query plan and choose the best among them. So, query tree came from algebraizer to optimizer, and SQL Server started the first stage, which called pre-optimization. It tried to do simplification, do some syntax transformation to get the query simpler, but not changing the query logic. And SQL Server at this stage loads statistics about the, not the column statistics, but the table rows count. And at this stage, SQL Server is trying to search for trivial plan. When SQL Server finds trivial plan, it means that there is obviously one best way to execute this query. There are not a lot of alternatives, and all alternatives are worse than this particular query plan. If SQL Server found the trivial plan, we are going to the execution stage right now. If the trivial plan was not found, SQL Server moved to the next phase of optimization, which called search zero. On this stage, SQL Server loads statistics, column statistics about the data distribution, and SQL Server start query plan exploration. Actually, SQL Server builds several query plans and compares their cost. Mostly on this stage, when SQL Server tries to join tables, mostly it will consider nested loops. And okay. After all, after this stage, SQL Server will return transaction processing plan. Let's talk a bit more about query plan alternatives. So, let's say we are executing this query on the Stack Overflow database, and this query is getting data about users and their posts for a user named Jon Snow. I'm trying to simplify this approach, but we have two tables, users and post. One way to execute this query will be getting data from users and then join posts. Another approach will be taking data from posts table first and then join table users. If we are considering one join physical join type, there will be two alternatives, but there can be more. SQL Server has 3 physical join types, but I'm omitting this right now. Okay, 2 tables, 2 options. Let's say we have 3 tables. How many options to get the data will we have? 6. For 4 tables it will be 24 options. Now you understand how big it could be. For 10 tables it will be pretty big amount of options. And this is factorial complexity, and you know that SQL Server is not limited by 10 tables or 20 tables. It can join more than 100 tables with enormous amount of permutations. Yes? How SQL Server can do this so quickly? Because it's not easy to follow all that path and choose the best one among them. SQL Server use the approach which called dynamic programming. This is how it works. This is simplistic view, but you will get the idea. Let's say I would like to join 4 tables, A, B, C, and D. This is the way and the complexity of joining all of them and following all that path. Now what SQL Server is doing. We have 4 tables, A, B, C, and D, and SQL Server check the optimal path for the beginning of this journey. SQL Server identified that A and B is the best tables to start from. So now we do pruning of search space. All options where the query plan will start from C and D is not considered from this point. Next, SQL Server do combinations of table. A, B will be the optimal path. So AC, AD, BC, and so on will not be considered from this point anymore. Now we're joining third table. ABC will be the best path. SQL Server do pruning of search space again and avoiding a lot of results. So in the worst case, the complexity will be exponential. But it really depends on how aggressive database engine is pruning the search space. For us, it means that SQL Server can do a very good job and can compile query plan very quickly, even for very complex queries. But at the same time, this means that SQL Server is pruning too many options for query plan. And my point here is that in any case, we are not 100% sure that the best plan was chosen. So we will talk a bit later about this on the demo. Now let's go to the next stage. If query plan, which was get on search 0 phase, does not satisfy the internal criteria, SQL Server is going to the next phase, which called search 1. On this phase, all transformations available, SQL Server tried to build a lot of alternatives based on its own rules, and also on this stage SQL Server estimates parallel plan. Right now it starts building 2 branches, parallel plan and non-parallel, and then compare their cost after all, which one will be better. On the parallel plan estimation, 2 parameters affect the parallel plan estimation: max degree of parallelism and cost threshold for parallelism. If the plan SQL Server get after search 1 phase satisfy internal criteria, it returns this plan and starts executing. If it's not, we're going to the last phase, search 2. This will be definitely the last phase, and SQL Server have to return the query plan after this phase in any case. So on this stage, SQL Server apply a full set of optimization rules, which it can't apply. Serial or parallel plan decision was made before, so on this stage, SQL Server do only one estimation for parallel plan and for serial plan. Also, if there is an enterprise edition of SQL Server, it will try to use and consider indexed views for the query. And as I said previously, it have to return the query plan. But there can be several reasons of returning the plan. First one, all planet checks were done, so in this case we probably are getting the best query plan possible. Second one, which called good enough plan was found, it means that the plan satisfy internal criteria for plan cost, but not checks were done. Third one is timeout. It means that SQL Server did not get the query plan which satisfy internal criteria for cost, but it have to return the query plan because it's spending too much time. Honestly, it's not time, but amount of permutation. It's limited, and when SQL Server exceeds this amount of allowed permutation, it returns the best query plan it has at this moment. The reason of query plan return will be timeout. And the last one, which is very rare, not enough memory. It means that SQL Server don't have enough memory to do the permutations and for compilation. I said that this is rare because when you see this, probably you will see another issues and many more other issues than just single query plan compilation. Okay, now it's time for a small demo. As I said previously, we can't be sure that SQL Server choose the best plan because a lot of query plan alternatives are pruned. So in this demo, I will use database wide word importers. Please do not try to find any sense in this query. It was built just to be heavy and big. I'm interested in this demo in the query execution statistics. So you see this query is executing for how many time? For 4 seconds. CPU time spent also almost 4 seconds. Now let me try to enable trace flag 8780 for this query. This trace flag increase the amount of permutation SQL Server can use during optimization, which means that SQL Server will have more time for query plan compilation and will have more chances to build the best query, to find the best query plan. Let me run this query again. Now you see that it's taking more than 4 seconds. You might ask me why this can be better. I will answer you later when we will check the results of the query. So, and while it's running, I would like to remind that this is a pre-recorded session and right now I'm with you in the chat, ready to answer all your questions. So this query executed in 32 seconds. And you see that compilation time is 29 seconds. And the actual execution time is 2.7 seconds, as well as CPU time, which means that we got the better query plan. Well, we spent more time on compilation. We can't use this query trace for this query as a persisted solution, but right now at this point we know that better query plan exists. We can use it. Right now it's in the cache. You see we are not spending time for query compilation and our query is taking 2.7 seconds, which is 1 second, more than 1 second better than previous one. So it will give you idea how the query plan could be. You can modify the query to get that query plan. You might use hints to get that query plan. Or another option, you can create a query plan guide to freeze this better query plan for your query. Okay, and let me get my options back. Why I was tried this query trace? Why I ever considered it? I will not run it for every query, but if I will create the query plan, and in the query plan I will see that the reason for early termination of optimization is timeout. this is the sign for me that I can use query plan, query trace, trace flag 8780 to validate if SQL Server can build better query plan for this query if it has more time for this. Okay, let's go back to the slides. We finished with query processing, and now SQL Server have to execute the query. Actually, it has to take the data and return data to the client. And this is the area of storage engine. This component is responsible for fetching data from disk and memory and sending it to the client. Okay. The entry point for storage engine will be component called access method. So SQL Server executor called different access methods. Access methods component called buffer manager to get the data. Data in SQL Server stored in the pages, data pages, 8 kilobytes in size. So each data page has 8 kilobytes. And the data, if the data is in memory, in data cache, SQL Server just returns this data. If it's not in the data cache, SQL Server has to fetch this data from disk, from database file. So it's going to database file, fetching data to the memory, and then return the data. And this page, you see that this page, when it was fetched from disk, it stays in memory for a while, until SQL Server will not decide to put it back to the disk and throw out from memory. Okay, that's how select works. But what if we need to modify the data? In this case, we have one more component in our schema which is called transaction log. So the access path is the same access methods buffer manager, buffer pool, and data modified in the data cache. After that, log manager component called, and the purpose of log manager is to persist the data. For this purpose, log manager write the modified data in the log buffer, and when transaction is finished, data from log buffer is going to the transaction log, which is a persistent storage for the data. After that, confirmation going back, and the data modification operation consider it as finished, only when the data is in transaction log. You see that no modifications to database file were made so far. That's because data modification confirmation does not require write to the database file. SQL Server can do that asynchronously with background processes, which called checkpoint or lazy writer. Why SQL Server do it this way? There are several reasons. First reason, that data in database file spread randomly. So to write data to the database file, we need to do a non-sequential write. Transaction log is some kind of queue when we're adding the data to the tail of the transaction log. So it will be always a sequential write. It's more efficient, it's faster, and in any case, your modified data stays in memory. So when you will read the data, it will be read from the memory. So no need for immediate saving data into the database file. Okay, and one more point I want to highlight here is when data is going from the log buffer, small piece of memory inside SQL Server buffer pool, to the transaction log. First case is when transaction finished. Insert, update, delete can be considered as a transaction as well. Second one, when log buffer is full, so transaction is pretty big and log buffer is small, it's 64 kilobytes. So when transaction fill the log buffer completely, these 64 kilobytes is going to the transaction log immediately. Okay, and third case, when background process checkpoint starts, it also flushes the log buffer. Okay, and one more component in this schema is missing. When we are doing modifications to the data, when we are selecting data, SQL Server needs to handle concurrent workload. Several connections, several queries are executed simultaneously. So SQL Server handles this concurrency with logs. And log manager component is the main part of this process. How logging is working? So first, there are several types of logs, and first and the most common is shared log. When SQL Server reads the data, it puts shared log on the row. If other process wants to read the data, it also puts shared log on the same row. They can read the data simultaneously without blocking each other. But if somebody wants to modify the data, that process will try to put exclusive log on the row, and it will wait in the queue because it can't put exclusive log when there are shared logs or any other logs on that row. What I'm describing right now is default SQL Server isolation level read committed. Logging behavior is changing in different isolation level, but this topic is outside, is not in the context of this session. Second type of log is exclusive log. When somebody wants to modify the row, the process needs to put exclusive log on this row. And when exclusive log is there, no other process can access the data. No exclusive logs, no shared logs. When the log is gone, next process from the queue will get access and will have a chance to put a log on that row and do its job. Okay? And third very common log, which called update. This is some kind of transient log. When the process wants to update the data or delete the data, SQL Server needs to find all that rows first. And SQL Server will mark all that rows which it wants to update with update logs. During this search phase, other processes which want to update records will stay in the queue because update logs are not compatible. But if somebody wants to read the data and put shared log on the row, that process will be allowed to do that. So it can read the data while first process is searching for the data to update. Okay? After all the rows found, SQL Server is converting update log to exclusive log to do actual data modification. And if there are shared log on some of the rows, that conversion cannot happen until shared log release. When shared log released, update log converted to exclusive log, and here the data modification is starting. And after that, no other processes can access the data. No update log, no shared logs. Okay, now it's time for a small demo where we will see the locking behavior, and the best illustration for the locking and blocking will be deadlocks. So for this demo, I have two queries. First one is a simple select ID, name and location from table users, where name like Santa. Okay. I'm using Twitter database for this demo. It has two main tables, users and statuses. Statuses is the Twitter posts which user post on Twitter. So first one is select query. Second one is an update query. For a single user where ID equals something, I'm doing two updates in one cycle, because if I will update Santa to Santa, SQL Server is clear enough to not do that job at all. So I will not refuse the deadlock. I'm using default isolation level read committed, and I'm just cycling this query with an infinite loop. Let's start the first one and the second one. After some time, one of the query will fail. So you see that this query was deadlocked with some other process, and so on and so on. SQL Server is trying to kill the query which is easier to roll back, the smallest query. In our case, if deadlock is between update and select query, this will be always select, because there is not much to roll back from transaction log in this case. So I have created a session which called deadlocks, and now I should have my deadlock information there. I'm collecting single extended event which called XML deadlock graph. Let's see the information about these deadlocks. Okay, you see, these bubbles are the queries. This is an update. This is a select. This is a victim of deadlock. And rectangles are resources for which these queries are competing. From what we see from this picture, select query holding the lock on index by username on the table users, and requesting shared lock on the primary key on table users, which is clustered index. At the same time, update query holding exclusive lock on the primary key and requesting exclusive lock on the non-clustered index. So, what is happening here? If we will check the schema, we will see that this table has three indexes. PK user is clustered index, and U user's name is unique non-clustered index. To get to the root cause of the deadlock, we need to check the query plans for our queries. Here is the query plan for select. You see that SQL Server is getting data from non-clustered index first, and then doing key lookup to clustered index. Yes. How we can read this query plan? SQL Server starts execution from the head of the query plan, and each operator in this pipeline has three methods: open, close, and get row. So SQL Server call open from this operator, then call get row. This operator does not have any rows, it doesn't do any data access, so it requests data from the next one in the pipeline. Nested loop also don't have any rows, it requests data from the next one. So this operator index seek fetch data from the database. And to do this, SQL Server put shared lock on the rows this query will read. Due to the logic of the nested loop, after receiving row from this input, it will do key lookup to this operator. And here it will put shared lock on the clustered index on the table users. And there is a small period of time between these two operators. And in this small time, another query, in my case, it is an update, put the locks on that indexes vice versa. First lock on the clustered index, second lock on the non-clustered index. Let's check the query plan for the update. You see this operator, clustered index update. This is where update is happening. And if we'll go to the properties, you will see that it put first lock on the clustered index and second lock on the non-clustered index when it updates the record. So it's doing it in different order, and we have this deadlock. Because two resources, clustered and non-clustered index rows, requests in different order. What we can do here, now we got the root cause of the deadlock, and I believe after getting the root cause, we can fix the deadlock. And we can find a lot of solutions to this deadlock. So, we are using read committed isolation level. Maybe we can consider using read committed snapshot isolation level, which will fix this issue. Maybe we can use no log here. Maybe it will be fine for this logic. I am not sure. Maybe we can find another way. Let's see what SQL Server is trying to look up here. It's trying to look up location, just one column. Because when we are building index by name, clustered index key, ID in our case, will be included explicitly in that index. And if I will remove location from my query, you see, there is no lookup right now, just indexing, because all data we need in this query is in the non-clustered index. And this also can be a solution if we don't need the location column. We can include location in the non-clustered index as an included field. This will also remove that key lookup, and there will be no deadlock. So you see, when we got the root cause of the deadlock, we can do a lot. We can find a lot of solutions. And this is beautiful. I love deadlocks and deadlock solving. And now you know how storage engine do this, and when we're requesting some data to handle concurrent load, SQL Server will use logs. In any isolation level, it will use logs, and it's very important to know how this works and how SQL Server apply the logs. Okay. So, what's next? And now, all data, we received the data which we requested, and SQL Server is ready to give it back to the client. It's almost the end of our path, but we did not talk a lot about SQL OS. It stays a bit aside of other components like query processor and storage engine, but it's very, very important because SQL OS is the component which allows query to execute. When query is executing, it needs system resources. It needs memory, drive access, I/O, but the most important resource is CPU. When query got CPU, it's executing. And the purpose of SQL OS is to manage resources and give the requested amount of resources to the query. When we start our execution, connection is created, and we can track the connection in the SQL Server with DMVs, Dynamic Management Views. For each connection, SQL Server creates a session. For each session, SQL Server creates a request. All these objects can be tracked with DMVs. And request is actually our query which we are executing. For each request, SQL Server creates one or several tasks. It depends on that fact if query is parallel or not. If query is not parallel, it will get one task. If query is parallel, it will get a task for each thread. And for each task, SQL Server have to give a thread from a thread pool. It's also called worker. And worker can be in three states. First one is running. It means that the query gets CPU time and all the resources and it's executing right now. Second one is suspended. It means that query is waiting for some resource, for memory allocation, for disk write, and so on and so on. The time which workers spend in suspended queue, also called wait time. And the last state is runnable. It means that query got all requested resources and now is waiting for CPU time. And CPU time allocated in SQL Server with an object called scheduler. So scheduler is responsible for CPU time for queries. For each logical CPU in system, there will be a scheduler inside SQL Server. And SQL OS is a component which handles all of these, which actually executes the query. For CPU, scheduling SQL Server use principle which called cooperative multitasking. This is how it works. We have some queries in our queue and we have a bunch of CPUs on the server. Free CPU is taking query from the queue and starts executing. When the query is in the queue, it's runnable state or runnable queue. When the query is on scheduler, it's in running state and it's actually executing. And executing has a time quantum. What it means? Time quantum in SQL Server is 4 milliseconds. When query is finished, this CPU can take another query from the queue. But if query is not finishing in 4 milliseconds, the query itself yields and is going to the end of the runnable queue and waiting the next cycle to continue its execution. This is called cooperative multitasking. So the process itself, the query itself, is responsible for yielding and giving resources for other queries to execute. And SQL OS is handling this. Okay. Let's talk a bit more about waits and how logs are working in this picture. I'm trying to show two components, Log Manager from Storage Engine and SQL OS. How SQL OS is doing this, how SQL OS is executing the query, how SQL OS is working with logs. Right now you see them in one picture, in one slide. Let's say I'm executing query, select stuff from user with a name like T. SQL Server puts shared log on the row and starts executing the query. Then I'm updating users and set name team PPP price where name equal team price. This is the real story. In UK, team price was very bored. Not bored, but he was tired from telemarketer's call, and he changed his surname to PPPP price to make some troubles for telemarketers to call him again. So For doing this update, SQL Server have to put exclusive lock on the third row. And SQL Server can't do that because there is a shared lock on the row right now. In this case, SQL Server will put this query in the suspended queue with the wait type lock mx, which means that this query is waiting for exclusive lock. When first query is finished, lock is gone, second query can continue its execution, and it's going to the runnable queue and waiting for the CPU time. When the scheduler is free, it's taking the query and continue execution. At this moment, exclusive lock put on the row and the query is executing and doing the actual update. Okay. Now we are at the end of our path. We started from query sent to SQL Server using TDS endpoint, and now we are on the moment when SQL Server is sending data back. It's sending the result set, the actual rows, which we can handle in our application, which we can see in our management studio and other tools. And at the end of the session, I would like to share one more interesting thing and interesting point, because something on this picture is missed. I do this to show it in the end and show it in the demo. SQL Server has one more endpoint, which called DAC, or Dedicated Admin Connection. SQL Server handle small amount of resources, small pool of CPU time, memory, and specific endpoint for these purposes. When by some reason you can't access SQL Server with regular endpoints, maybe SQL Server is overloaded, maybe it doesn't have enough CPU, enough threads in pool, enough memory, you always have this backdoor dedicated admin connection to connect to SQL Server and find what's going on there and maybe fix the issue. And right now on the demo, we will go through the dedicated admin connection and we'll try to check what's happening in the overloaded SQL Server. At the beginning, I will run the blocking transaction, which will create some workload on the server. And first of all, I will remove this set statistics time and IO, which I have by default in my management studio, to not mix the results with the query. Okay, I'm running blocking transaction in VentureWorks database. I'm running transaction, and then I'm doing update of big product table. I'm not doing any commit or rollback. Okay, so this transaction is open, and right now I'm ready to start my workload. This batch is creating 1000 threads, which are trying to request data from SQL Server simultaneously. Now let's try to check what's happening on the server. And you see that my connection is not opening. I can't receive the connection by connecting with the regular endpoint. Because this workload which I run exceeds the limit of thread pool inside SQL Server. All threads were taken by those queries, and I don't have free thread to execute my queries right now. So you see that error, and I can't get to SQL Server with the regular connection. I will try to do this with dedicated admin connection. I'm doing this by writing admin colon before the server name, and also my user should have sysadmin permissions to connect with dedicated admin connection. And the connection is opened immediately. Right now I can explore server, I can do all this stuff. I don't have IntelliSense, by the way, because IntelliSense is a separate connection, but dedicated admin connection can only be single. Okay, I'm checking data about current executing queries with dmexec requests view and dmexec SQL text for getting the query text. And you see that I have a lot of select stuff from big products queries, and these queries exceed my thread pool. Also here I see that all of them are in suspended state, which means that they are waiting for something, and they are waiting for log ms, which means that they are waiting for a chance to put shared log on the rows to read that rows. And also this view dmexec request contains information about session ID and blocking session ID if one session block another session. All of them you see blocked by session 52, which is not very true because select query is not blocking select query. But session 52 has blocking session ID 88, and this is the real head of blocking chain. We need to investigate that and check that session. We don't see session 88 in the list. You see 52 and then next is 90. And this list is ordered by session ID, which means that this session definitely exists because it holds some log and it's blocking our queries. But that session has no active queries. Let's check it in the dmexec sessions where session ID is 88. Okay. You see that session exists, it's run from my management studio, and this session is in sleeping state, which means that session is open, connection is open, but there are no queries executing in this session right now. What we can do in this case, we can simply kill this session, but the better way is trying to investigate what's happening inside. There are no queries, we can't see that information, but in dmexec connections, we have a column which called most recent SQL handle. So we can get the last query executed in that session. We are running the query and see that this is the text. Oops. Anyway, this query was executed in that session. Now we can make a decision. Should we wait for something or we can kill that query? I think in this case we can kill session 88, and after this session was killed, if we will get back to our queries, you see that they are started their execution. And some results appeared. Okay, this is how dedicated admin connection can help in troubleshooting overloaded SQL Server, and this is a beauty of SQL Server and its components. Okay, at this point, our journey inside SQL Server is coming to its end, and during this session we went through all SQL Server main components: SQL Server network interface, query processor, storage engine, and SQL OS. Now I would like to thank you to Microsoft for supporting Data Platform Geeks and Data Platform Summit. Thank you for attending my session. Please follow these 3 ways to win prizes and follow Data Geeks and Data AI Summit on Twitter. At the last word, I would like to say thank you very much for attending my session. And since I'm from Ukraine, you know that there is a war happening in Ukraine, and I hope that when you see this session, the war is over and everything is good. But if it's not, please support Ukraine, donate to local funds, spread the word, and so on. Thank you very much for attending my session. Enjoy Data Platform Summit. See you.